Okay, today let's have a look at the third lesson of chapter 5, applications of vector addition and resolution geometrically in two space. Okay, first let's have a look at today's learning goals. After this lesson, you are expected to be able to understand the concept of equilibrium vector in two space. Find the resultant vector and its equilibrium geometrically in two space. Resolve a vector into rectangular components geometrically in two space, and then solve application problems related to vector addition and resolution geometrically in two space. Okay, now first let's have a look at the applications of vector addition. Two vectors that are perpendicular to each other and add together to give a vector v are called the rectangular vector components of v. So let's have a look at the two examples here. Draw the resultant for each set of rectangular components. Then calculate the magnitude and direction relative to the horizontal vector of the resultant. First, a sailboat's destination is 8 kilometers east and 6 kilometers north. Second, in the numerical model of the Bay of Fundy, the velocity of the water is given using rectangular vector components of 2.5 meters per second northwest and 3.5 meters per second southwest. Okay, I'll give you 4 minutes to have a look at these two questions. Can you find the resultant vector? Okay, let's have a look at the solution. First, keep the vectors head to tail. The resultant vector R is the hypotenuse of the right triangle. Use the Pythagorean theorem to calculate the magnitude of the resultant. We have the magnitude of R squared equals 6 squared plus 8 squared. Therefore, the magnitude of R equals 10. Then we can calculate the angle that the sailboat makes with the direction east. Theta is arc sine 6/8, which is approximately 36.9 degrees. Since this situation involves navigation, calculate the direction as a bearing. find that the bearing is 90 degrees minus 36.9 degrees, which is 53.1 degrees. So the resultant displacement is 10 kilometers at a bearing of about 053.1 degrees. Now, do you have any questions? Okay, if no questions, let's have a look at the question B. We can use a parallelogram method to draw the resultant. Use Pythagorean theorem to calculate the magnitude of the resultant. We have r squared equals 3.5 squared plus 2.5 squared, which is about 4.3. So next, let's find the value for theta. Okay, so here we need to make a modification that gives us magnitude of r is about 4.3, not r squared, right? Okay, next find the value of theta. So theta is arctangent 2.5 over 3.5, which is about 35.5 degrees. Then since the 3.5 meters per second vector is 45 degrees below the horizontal, r is 45 minus 35.5 or 9.5 below the horizontal. This is 90 minus 9.5 degrees or 80.5 degrees west of south. So the water velocity is about 4.3 meters per second. West of south, 80.5 degrees. Okay, any questions? All right, then let's have a look at another important concept, which is called the equilibriant vector. An equilibriant vector is one that balances another vector or a combination of vectors. It is equal in magnitude, but opposite in direction to the resultant vector. If the equilibriant vector is added to a given system of vectors, the sum of all vectors, including the equilibriant, is zero vector. So, for example, in the following diagram, the resultant vector of F1 and F2 is R, and E has the same magnitude with R, but with opposite direction. So vector E here is called the equilibriant vector of R. Are we clear? Okay, so let's have a look at an example. Find a resultant and its equilibriant. A clown with a mass of 80 kilograms is shot out of a cannon with a horizontal force of 2000 Newton. The vertical force is acceleration due to gravity, which is 9.8 meters per square second times the mass of the clown. Question A, find the magnitude and direction of the resultant force on the clown. Question B, find the magnitude and direction of the equilibriant force on the clown. Okay, I'll give you 5 minutes to have a look at this question by yourself. Okay, have you finished? Let's have a look at the solution. So we can draw a diagram of the situation. So vertical force is 9.8 times 80, or 784 newtons downward. To find the resultant force F, we can add the two vectors, right? Since the force is perpendicular, we can use the Pythagorean theorem to find the magnitude of the resultant force. The magnitude of F squared equals 2000 squared plus 784 squared, which is 4614656. Therefore, the magnitude of F, the resultant force, is about 2148. The magnitude of the resultant, well, can also approximate to 2150 newtons. To find the direction of the resultant force, we can use the trigonometry. And let theta represent the angle of F to the horizontal. Then we have the following relationship. Tangent theta equals 784 over 2000. Then theta equals arctangent 784 over 2000, which is approximately 21 degrees. Therefore, we have the following conclusion. The resultant has magnitude about 2150 newtons and direction of 21 degrees below the horizontal. Okay, have a look at this solution. Do you have any questions? Okay, then let's have a look at question B. We can draw the equilibrium on the diagram, which is shown here as the vector highlighted in blue. The equilibrium has the opposite direction with the resultant force, but with the same magnitude of the resultant force, which is also 2150 newtons. So the equilibrium has magnitude about 2150 newtons and direction of 159 degrees counterclockwise from the horizontal. Okay, any questions? Okay, so if no questions, let's have a look at some other related concepts. The directions related to vessels and flights. So we have the following concepts we need to be careful with. Heading is the direction in which a vessel is steered to overcome other forces, such as wind or current, with the intended resultant direction being the bearing. So we have the following relationship. The heading of the vessel plus a wind or current direction, the vector standing for the wind or current, equals the actual bearing, which is the direction of the resultant. In flight, we have the ground velocity, air velocity, and also the wind or current velocity. Ground velocity is the velocity of an object relative to the ground. It is resultant or bearing velocity. When the heading velocity or air velocity and the effects of wind or current are added, again, we have the following relationship. The air velocity plus the wind or current velocity equals the resultant velocity, which is called the ground velocity. You understand? Okay, then let's have a look at some example. First, solve a flight problem. It is known that an airplane is flying at an airspeed of 500 kilometers per hour on a heading of 040 degrees. A 150 kilometer hour wind is blowing from a bearing of 120 degrees. Determine the ground velocity of the airplane and the direction of the flight. Okay, according to the directions related to vessel and flights we have just learned about, can you try to solve this problem? Okay, I'll give you 5 minutes to think about this. Okay, have we finished? Let's have a look at the solution. So we can redraw the diagram showing the resultant, like in here. We can let our vector r be the resultant ground velocity of the airplane. And let theta be the angle the resultant makes with the wind direction. And then we can use the cosine law to solve for the magnitude of r. And the cosine law tells us the magnitude of r squared equals 150 squared plus 500 squared minus 2 times 150 times 500 times cosine 80 degrees. So we can solve. The magnitude of r is about 496.440. Also, we can use the sine law to calculate the value for theta. So we have the following relationship. Sine theta over 500 equals sine 80 degrees over 496.44. And then theta is approximately 82.689 degrees. Any questions? Then to determine the bearing, we can translate the resultant. So its tail is at the origin of the compass quadrant. The head of the origin wind vector is 60 degrees off 180 degrees. So the head of the translated wind vector is 60 degrees off 360 degrees. Therefore, in this diagram, as we can see here, alpha is 82.689 minus 60 degrees, which is 22.689 degrees. Therefore, we have the following conclusion. The airplane is flying at a ground velocity of about 496 kilometers per hour on a bearing of about 0 to 3 degrees. Remember that if it does not specify whether it's a quadrant bearing or true bearing, by default, this means true bearing, right? Okay, have a look at this question here. Do you want to ask anything? Any questions? Okay, if no questions, let's have a look at another example. Solve a tension problem. So here we have a traffic light at a intersection. It's hanging from two wires of equal length, making angles of 10 degrees below the horizontal. The traffic light weighs 2,500 newtons. What are the tensions in the wires? Okay, I'll give you 5 minutes to have a look at this question by yourself. Then we'll have a look at the solution together. Okay, have you finished? Any ideas? Okay, let's have a look at the solution together. We can draw a vector diagram so that the two tension vectors are keeping the traffic light at equilibrium. Then we let T1 and T2, the two vectors, represent the two equal magnitude tensions. We know the 2500 Newton downward force of the traffic light is a equilibrium vector. So find the resultant of these tensions in the wires. We have we redraw the diagram to show the sum of the tension vectors with the resultant of 2500 Newton upward, like it shown here in this diagram. Then we know the equal angles at the base of the isosceles triangle. Each measure 180 degrees minus 20 degrees over 2, which is 80 degrees. Then we have the following relationship. The magnitude of T1 over sine 80 degrees equals 2500 over sine 20 degrees. Then we can find the magnitude of T1 is 2500 times sine 80 degrees over sine 20 degrees, which is about 7198. The unit is Newton. Therefore, we say the wires each have a tension of about 7200 newtons at 10 degrees below the horizontal. Okay, any questions? All right, if no questions, let's have a look at another example. Okay, before we see another example, let's have a look at a concept of resolution of vectors into rectangular components. So a vector can be resolved into two perpendicular vectors whose sum is a given vector. This is often done when, for example, both vertical and horizontal forces are acting on an object. These are called the rectangular components of the force. So consider a vector v at an angle of theta to the horizontal, as shown here in the bottom left. It can be resolved into rectangular components VH, which stands for horizontal component, and VV, which stands for vertical component, where V equals VH plus VV. So this is how we can resolve a vector into rectangular components. Okay, now let's consider this example. A tow truck is pulling a car from a ditch. The tension in the cable is 15,000 newtons at an angle of 40 degrees to the horizontal. Draw a diagram showing the resolution of the force into its rectangular components. Then determine the magnitudes of the horizontal and vertical components of the force. Okay, again, I'll give you 5 minutes to have a look at the example here. Okay, have you finished? Any ideas? All right, let's have a look at the solution together. So as shown here in the graph on the right, the tension can be resolved into two rectangular components. The vertical, which is denoted by FV, and the horizontal, which is denoted by FH. And we know that FH plus FV equals the resultant force. And in this right triangle, we have the following relationship. Magnitude of FH over cosine 40 degrees equals 15,000. And this gives us the magnitude of FH equals 15,000 times cosine 40 degrees. And this is approximately 11,490. The unit is Newton. And the magnitude of FV is 15,000 times sine 40 degrees, which is about 9,642 newtons. So the magnitude of the horizontal component is about 11,500 Newton. And the magnitude of the vertical component is about 9,600 newtons. Okay, any questions? Okay, no questions. Let's have a look at the last example of today's lesson. Find the rectangular components that are not horizontal and vertical. A box weighing 140 newtons is resting on a ramp that is inclined at an angle of 20 degrees. Resolve the weight into rectangular component that keeps the box at rest. Okay, again, I'll give you 5 minutes to have a look at this example. Okay, have you finished? Okay, let's have a look at the solution. Okay, so a box weighing 140 newtons is resting on a ramp. So we can draw a diagram to illustrate this problem as shown here in the figure on the left. The object is at rest in the directions of both perpendicular and parallel to the ramp, right? According to the Newton's first law of motion, we have the following relationship. First of all, the magnitude of N, which is a supporting force from the ramp, equals 140 times cosine 20 degrees, and this gives us about 131.6 newtons. On the other hand, the magnitude of the friction, F, equals 140 times sine 20 degrees, and this is approximately 47.9 newtons. So the box is kept at rest by a force of 131.6 newtons perpendicular to the surface of the ramp, and by a friction of 47.9 newtons parallel to the surface of the ramp. Okay, any questions? All right, if no questions, that's the end of today's lesson. Before we leave, let's keep it revisiting the learning goals. So after this lesson, now you should be able to understand the concept of equilibrium vector in two space, and find a resultant vector and its equilibrium geometrically in two space. Resolve a vector into rectangular components geometrically in two space. And last, solve application problems related to vector addition and resolution geometrically in two space.